Hello everybody and welcome to the first video in our right triangle trigonometry series. Today we're going to look at something called the tangent ratio, and we're going to focus on determining angles using this tangent ratio. The first thing we should discuss is a right triangle itself. Now, the defining feature of a right triangle is the 90-degree angle that it contains. So this box here means it's a 90-degree angle. You won't see 90 degrees listed in the triangle. You'll see a little box like I have there in red, and then you'll know you're dealing with a right triangle. Now, they also like to name, or often when we have triangles, we associate letters to their corners and we name the triangle. So traditionally, you'd name it something like this. We'd use A and B on these outside angles, these non-right angles, which would be acute, by the way, meaning angle A and angle B. The size of their angles are going to be less than 90. And then traditionally, we put C in that right angle position. The next thing I want to talk about is names that you're going to see come up. Now, we're going to use names like opposite side, adjacent side, hypotenuse, all that kind of stuff. So I want to talk about that. Now, one thing you may remember from dealing with Pythagoras is that the across from the right angle is the hypotenuse. All right, so that's always a hypotenuse. It is the longest side, and it is opposite the right angle. So opposite, I'm going to write this down, really means across in a right triangle. Okay, and then we're going to have another phrase, adjacent. That means beside in a triangle. So now we'll name opposite. Oh, sorry, I didn't finish my first thought about on the right triangle. We have a hypotenuse, and then you likely remember this being a leg and this being a leg. So the other two sides are called legs. So we have two legs and a hypotenuse in every right triangle. Now, what we're going to be doing, I'm going to pick another color here. Let's go orange. Is you're going to be naming things. Oops, that was supposed to be orange. You're going to be naming things opposite leg or adjacent leg based on the angle you're starting from. So from angle B here, I would call this leg over here the opposite leg because it's across the triangle, and I would call this leg here the adjacent leg. All right. Now that's looking kind of busy, so over here I'm just going to draw one more right triangle. Put my 9-degree in here. Put the same letters in, A, B, C. And if I wanted to start from this angle A this time, this then would be the opposite leg, and then whatever's right beside it is the adjacent leg. And then, of course, across from your right angle, across from that right angle is always your hypotenuse. So there's no one side that is always the opposite leg or the adjacent leg. It's relational, so it means based on the angle you're dealing with, then you start naming if something is opposite or adjacent. Okay, so that is a right triangle and a few other tidbits I threw in there. So the first ratio we're going to look at, or the first thing in this right triangle trigonometry we're going to look at, is something called a ratio, and it's a tangent ratio. So remember that a ratio, picking my color, sorry, a ratio is simply when you compare two or more things. All right? So we're going to be always comparing two sides of this right triangle. And by comparing these two sides, we can find missing side lengths or missing angles. So it's kind of neat that we can find all these missing pieces from these right triangles. So we're going to look at three ratios in this unit. This is the first ratio we're going to look at is the tangent ratio. So I've written this out with a lot of words here. Typically you wouldn't see it written like this. I'll show you in a more short form here right away. But it says tangent ratio of angle theta. So we're going to start from this angle theta. Theta is just a Greek letter, meaning just starting from whatever angle we're talking about. It's always one of the non-right angles, though, just so you know, we're not going to ever work from the right angle. Okay? And the tangent ratio consists of comparing the length of the leg opposite the angle you're starting from to the length of the leg adjacent that you're starting from. Okay, now you'll also usually see it written short form, something like this, tan theta equals opposite over adjacent. Okay, so that is something you'll see lots, kind of a shorthand version of what I just wrote there. Okay, so that's the tangent ratio. Let's start playing around with it now. Okay, so in this first example, it says determine the value of each tangent ratio, or sorry, of the tangent ratio for each situation. Okay, so in this first one, I'm looking for the tangent ratio of angle D and then the tangent ratio of angle F. So angle D, I'll write here. So you might be thinking that is like a less than or greater than sign. But that is just a mini angle, and we write that, we put that angle sign and then the letter that, or the corner that we're dealing with. So this is angle D. That means I'm dealing with this guy right here. Now, for the tangent ratio, I'll just write out, again, we're comparing two sides, and when we compare the opposite leg over the adjacent leg, or to the adjacent leg, so this is the opposite leg, this is the adjacent leg. Whenever we compare those two things, then we know we're dealing with the tangent ratio. So tan D is what I'm writing, because now I've replaced this theta with D. So theta is always the angle we're talking about. Theta is just that general angle. Like if I don't actually have an angle, I'll just leave it as theta. But now we have an angle, D. And if once I've labeled, or once I know what angle I'm working from, then I can start naming things. So this is across my triangle. So that would mean this would be the opposite leg. And this would be right beside my angle. This would be the adjacent leg. Now, a good question that will pop up with people is, why can't this be the adjacent leg? Well, the reason that can't be the adjacent leg is because it's a hypotenuse, and a hypotenuse is not a leg. Okay, it's a different, hypotenuse is its own style of side length. These legs are a different type of side length. Okay. So now I'd plug my values in, 3/4, and that would be the value of the tangent ratio from this angle D. Just 3/4. If you wanted to convert it to 0.75, you definitely can. Let's look at now angle F. So angle F, again, tan theta equals, now they don't, I often don't write the leg part down, but you need to remember their legs, so I often just write it as opposite over adjacent. And now I'm dealing with this F over here, so it's going to be, okay, the tangent ratio from angle F, or just tan F. The opposite is now, again, it's across. It's always across. That part never changes, but the side length will change, because what is opposite, or what is across, depends on what angle you're starting with, right? So then that'll be 4. And then what's adjacent is right beside, so that would be 3. So the tangent ratio from that other angle is now 4/3. All right, and again, if you want to convert that to decimal, go for it. So that is finding the tangent ratio. So let's practice that a little bit more. Finding two more, like really, if you understand how to plug the values into the ratio, everything else is going to be pretty darn easy from there. So let's go back to blue. Angle X. So I will write tan theta out again, but now you can see I'm starting to get lazy. I'm just going to write O/A for opposite over adjacent. And like we said, it's angle X. So instead of tan theta, I'm going to write tan X. And here is my X, meaning this would be opposite, and this would be adjacent. Again, across the triangle is opposite, and right beside is adjacent. So that would be 6/12. And then again, you can now reduce that if you want to 1/2, 0.5, whatever you want to do there would be fine. Let's look at the next one. Angle Z. Tan theta equals opposite over adjacent. If you don't want to write this little first part down, you don't have to. You can go directly into just plugging things in once you're comfortable as well, everyone. So here's Z. So now my opposite changes. So now that's opposite, and this is adjacent, because 12 is across the triangle from Z, and 6 is right beside Z. So tan Z equals 12/6, or just 2, and there we go. Time to move on to our another example. So we go further than just finding the value of this ratio, this comparison, but we use that value to find missing elements, so missing angles or missing side lengths. In this video, because I just don't want it to be too long, we're going to look at missing angles. The other reason I'm doing it this way is the textbook we're following for our curriculum does it. So just to keep things kind of easier for yourself when you're using your textbook, I thought I'd just kind of match it up. So angle G now is what we're looking for. So it says determine the measure of the following angles. Before I just wanted to know the tan ratio from the angles. Now I want to know what is the size of that angle. And then I'm going to be looking for what is the size of J, the other angle. Okay, so angle G. First thing we do is we actually have to set up similar to what we were doing before. So opposite over adjacent, I'm going to find the value of my ratio first. Tan G equals, and here's G. So opposite would be 4, and then adjacent would be 5. Now, sorry about that little pause, everyone. I need a glass of water there real quick. Okay, so once we have our tangent ratio, now we're going to actually solve, or we're going to determine the value of this angle G. Now to go there, or to get to that point, there's two ways to do it. You can use your calculator, which has a chart programmed into it, or you can use an actual chart. So when I'm teaching this in class, I always begin with the chart. I thought it would be kind of difficult, though. I wasn't sure how I was going to do it with the software I had to kind of incorporate the chart. So I'm going to jump right to the calculator. But the thing to know is this. With right triangles, they are very, very, very predictable. So if you build a triangle like we did here, where I have this side of 5 and another side of 4, well then there's only really one triangle that can be built that way. And based on those dimensions that I have, it's predictable what this angle G will be and what this angle J will be. So these charts have all the answers already in there based on the properties that these triangles are showing us. So that's how those charts work. And like I said, your calculator is not magic. It just has a really big chart programmed into it. And your keystrokes are just telling it how to kind of sort through that chart and find the piece that you want. Anyway, let's get to solving now. Okay, so we want to find angle G. To find angle G, you're going to write this, inverse of tan, and then the 4 over 5 again. What you're really telling your calculator to do is to now go backwards. So it's kind of programmed to go one way. Typically, you're going to have that angle size, and it's going to go find the ratio. So if I said like the tan of some number, so tan of 50, if you plug that into your calculator, you're going to come out with some value. It's going to be a decimal. In this now, I'm wondering about what the value is. So this calculator has to go back. The calculator has to go backwards, so that's how I have to use this tan to the -1. Now, how to do that? Okay, so this is where you might need to talk to your teacher or talk to me, whatever the deal is. Different calculators use different logic. So there's kind of two main ways to do it. You either can, if you hit the tan button right now, and you see the word tan appear on your screen, that means you can always hit tan first and then the value, okay? If you are using a calculator like I am right now, where when I hit tan, it just kind of blinks, I don't see the word tan, that means I have to actually put my number in first, then tan. So the way I'm going to use my or what I'm going to do with my calculator right now is I'm going to type in 4 divided by 5, or seeing I can write that as a decimal, I might write 0.8. And then I'm going to hit second function. Now, what second function means, everybody, if you're new to these calculators, it just means that the buttons on your calculator have two functions. The main function, or the first function, the primary function, is whatever the button says. So it might have the number 1 on it, right? Or just tan. Above it, though, if I'm using that tan example, you'll see in some a different color of ink, you'll see tan and then to the -1. So that is the second function that button has. So if you hit second function, what it does is it enables all the second functions on that calculator. So whatever you hit now on your calculator, the second function will act. Sorry, that kind of sounded rambly. So back to what I was saying. I'm going to type in 0.8. I'm going to hit second. Then I'm going to hit the tan button. And really what it'll do, though, is take the inverse of tan for me. And when I do that, my answer kind of just jumps onto my calculator. And now I get 38.66. So sorry I've been taking so long to kind of talk about this. There's just some basic things we need to talk about the calculator. And after that, really, that's about everything for the chapter, really, it has to do with the calculator. Like once we figure the calculator out, nothing new will happen. The other way that calculator works is that for a lot of people, they will go second function, tan, and then type in the value 0.8 and then hit equals, and then you'll get the same thing, 38.66. Last thing to check on is that your calculator is set to degrees, not radians. Radians is a different way we can measure things, measure angles. So make sure you're set to degrees. There should be like a DRG button or some sort of button that will change the different settings for you. If that doesn't make sense, ask a friend or come talk to me. I can help you out with that. Okay, back to this. I got 38.66. Now, I want to find angle J, and we'll take a lot less time to do that. So now I'm going to write tan theta equals opposite over adjacent. Tan J equals, so now J is what I'm looking for. So remember, my opposite changes. So now it'd be 5 over 4. So that's my ratio, and that's great. I want to find if my tan from J, if the tan ratio for angle J is equal to 5 over 4, then I want to know what just angle J is equal to. So again, I'd write inverse tan 5 over 4. And I go to my calculator and I just type that in, and that calculator is going to search its chart that's already plugged into it, or sorry, programmed into it, and it'll tell me the answer. It'll tell me what value or what angle size is associated with this tangent ratio. So once again, I'm going to go 5 divided by 4, second function, tan. And I get, once I round, 76.96. Now I said 76.96. That can't be right. I'm using a phone calculator today, which is very bad, guys, because they're so hard to use. I should have 51.34. So what I would have done wrong on my phone calculator, and that's why they're not the best to use, I didn't use brackets, and when I typed in 5 divided by 4, it actually I took the inverse tan of 4, not the 5 over 4. So I should have used brackets or converted to a decimal. Anyway, the other way I could have done this is using a triangle property that you may or may not know. The angles of a triangle always add to 180 degrees. Now, we already know that angle H is 90 degrees. That means these two angles must add to the other 90. So what we can always do is just double check that. So 38.66 and 51.34. I might just write that out. 38.66, 51.34. Add that up, and actually that adds up perfectly to 90. Now, when you're doing that, because we're rounding, you may get like 90.01 or 89.98 the odd time because of our rounding. But if you actually extend that number out a little bit, you'll always get to your 90 here perfectly. Okay, so that is how we find the missing angles. You're going to see it's really repetitive for the rest of this topic, which is hopefully a good thing. So B, and again, I'm sorry it took so long. The first part there, we will move quicker now. So I'm going to write tan K equals, so I'm not going to write down my my general form. I'm not going to write tan theta equals opposite over adjacent. I'm just going to go right to it. So this is K, so then I'm going to have that's going to be 9 over 13. And then from there, I want to find the size of angle K based on the fact that tan of K is equal to 9 over 13. 34.70. Now we'll look at angle N. So that's going to be tan N equals, and that's over here. And again, now my opposite and adjacent change, so this will be 13 over 9. So based on the fact that the value of the tan ratio from angle N is 13 over 9, we can find the size of angle N itself. So angle N, I'm going to take the inverse of this tan, which is really just telling my calculator to go backwards, like I've said. And that would be then 55.30. And if you double check that, does that add up? That adds up, people. Okay. Now, you might be thinking, do I really need to use the tan ratio twice to find those angles? Seeing you just told me in the last slide that if I found angle K first, I could then just go, okay, well, 90 degrees minus angle K, right? And that would equal whatever angle N was going to equal. Yeah, that you absolutely can do that. But because we're just trying to learn this skill, I'm going to ask you to use the tangent ratio both times just to practice the skill. That's the only reason you would do it. You are right. Really, on a test or on a quiz, you definitely, or an assignment, you definitely can just use this rule here instead on the second time. But if you're talking, say, like basketball practice, oftentimes I do dribbling drills with 2 basketballs. That is not something that would happen in a game, right? But we do it just for the practice. Same here. We're going to use this tangent ratio, even though it's a little bit slower, just for the practice. Okay, example 3. So a situation here. So these questions are similar to the ones that are in your textbook. That's why I thought I'd choose one. The latitude of Fort Smith, Northwest Territories is approximately 60 degrees. Determine whether this design for solar panel is the best for Fort Smith. Now, something you need to know is that the angle in which you install this solar panel has to be about the same as your latitude. Okay? So if your solar panel angle is the same as this latitude, then everything's good to go. I guess it's optimal, it's as efficient as it's going to be. If it's not, then it just won't collect as much sunlight, so you're not going to get as much return on this investment. So one thing I also want to talk about is angle of inclination. So angle of inclination is, if this is me, and I have red hair, whether you know that or not, so it's kind of fitting I have drawn this with red. Angle of inclination is just the angle up, okay? The angle that something is increasing. So this is just an imaginary horizontal line that I've created, and if I'm looking up at, say, the clouds, wondering about math, I could then determine what the angle, maybe that I'm looking up as. So angle of inclination is the angle upwards. So here is my 90-degree angle. And we're just going to go through and see if we can find this angle of inclination, because that would be right there. And we'll see if this thing has been mounted or installed properly. So tan. Now, it doesn't have any letters A, B, or C, so by all means you can use that theta sign. That's just kind of your stand-in, your default angle. And opposite would then be 9 over 12. And we're looking for, now based on this fact that the tangent ratio from this angle theta is 9 over 12, we can then find angle theta. So angle theta is going to be equal to the inverse tan, 9 over 12. Again, we're really just meaning to our calculator, go backwards. And that would work out to be 36.87, meaning that this is not the best design. Okay? Not the best design. And if you're wondering why, again, we want the latitude to be approximately the same as the angle of inclination of your solar panel. And again, why I bring that up is because it has a question like that in your textbook, so I thought that was kind of strange, so we should maybe look at one. Let's look at one more. So in the previous example, there was a picture provided. That is not always the case. You have to draw your own picture often. So you'll have to imagine how a right triangle would resemble this situation. A 10-foot ladder leans against the side of a building with its base 4 feet from the wall. What angle to the nearest degree does the ladder make with the ground? Okay, well, I think it makes sense that a ladder leaning against the wall, so there's the ladder. I guess there's the wall, and this would be the ground. Now, I'm not drawing it to scale. I'm just kind of doing it quickly. So this would be my ladder. And it says side of a building, so I'm just going to call that a wall. And it's going to be, the base is always on the ground. So the assumption we will make in all of these questions is that walls or buildings, they always meet the ground at a 90-degree angle. Okay, everybody? So that we have an absolutely vertical wall or building meeting an absolutely horizontal ground. So it's a 10-foot ladder. So I can put 10 there. Let's maybe make that a different color. So that's 10. And its base, so the base of the ladder is 4 feet from the wall, so that would be here, because this would be the bottom of the ladder right here. So I could say bottom. I could say top right there. And now what angle to the nearest degree does the ladder make with the ground? So where the ladder and the ground meet is what I'm worrying about. So I'm wondering about what this angle B would be. So then tan B is equal to, well, my marker's not working here. Okay, so tan B is equal to opposite over adjacent, and tan B can stand, right, because I'm looking for B. Opposite, if you see here, I don't have the opposite. I have the hypotenuse, but I don't have the opposite. So either I messed up or I'm kind of stuck and can do something else, right? So think about it, think about it, think about it. Hopefully you thought, hey, why not just use Pythagoras? So what I'll do is I'll actually, first of all, I'm going to use the Pythagorean theorem, a squared plus b squared equals c squared, and that's going to help me find, this would be little b right there. Okay, and once I have that, then I can go back to my tangent ratio and complete the question by finding that angle b. So remember, a and b in the Pythagorean formula those are the legs. Sorry, I'm having trouble speaking tonight. Jeez Louise. Okay, back to it. They're the legs, and then the c is always the hypotenuse. So I guess I'll make a 4 squared plus this b, which will just stand as b squared, and c is the hypotenuse, so that is 10 squared. So now I just write out the things, or calculate what I know. Now I want to get b squared by itself, so I move the 16 over. So that would be what, 84. And then now I don't want b squared, I want b, so I have to take the square root of b squared. Whatever I do to one side, I have to do the other. So b is going to equal 9.17 when I round the 2 decimal places. And then I can actually just kind of go back to this and plug that in. So the opposite ends up being this 9.17 divided by the adjacent, which we already had, which was 4. So the opposite was at 9.17, the adjacent is the 4, and then now again, based on the fact that the tan ratio from angle B is equal to 9.17 over 4, which I would then convert to a decimal really if I was using one of these charts I spoke about earlier in the video. But anyway, so you can too, but if you are going to convert everything to decimals, make sure you carry a lot, like 5 decimals would be great. Anyway, inverse tan, and 9.17 divided by 4. I often don't change them to decimal. It just seems like extra work. I don't need to do that. When I'm doing my calculation, I'm going to put in 9.17 divided by 4, and my calculator will already convert that or automatically convert that to decimal. So for me, I think that's kind of a wasted step to convert it to decimal earlier than that. Anyway, once I calculate this, it will equal 66.43 degrees. So that would be the angle that this ladder has been set at, right? The angle of inclination. I'm going to write that down here too, inclination for this ladder. Okay, so that was a longer video, but we covered a lot of stuff here. The great thing about working with right triangle trigonometry is there's not a lot of unique logic going on, meaning how we use the tan ratio to find angles. We have the same logic for cosine. There's 2 other ratios, cosine and sine. And the way we use them is going to be the exact same thing as this. So it's going to feel like you already know it when we get to that point. Okay, everybody. If that didn't make sense, make sure you come talk to me or your teacher. I hope you have a great night, and I hope I can speak more clearly when I'm teaching you in real life. See ya.